Module number 6, we're going to have Brian kind of go through some of the conclusions and talk a little about the future innovations related to SDCL. Brian will be inviting other members of the panel to come in and help with some of these discussions. And then after the conclusion and future innovation discussion is complete, Paul will come back on, and he and I, if necessary, we'll try to get through as many of the remaining questions that we weren't able to get to during the other presentation.
Okay, great. So I ended my presentation with what we've done so far, and Jason alluded to the fact that we are working to get this added to our engineering policy guide. So MoDOT is going to continue to use SDCL where it makes sense, and in our preliminary design, we've been evaluating, based on our past experience with these 66 that we've already done, is this going to be cost effective to do this with simple for dead, continuous for live steel? I think we've even thrown out some alternates where we've had either a pre-stressed concrete or the SDCL steel type structure to see what the contractors prefer. But as I said, we did contract. We put out a request for proposals. We're a little short on internal staff for our policy development and AASHTO interpretations and all of that kind of stuff. So we did put out a request for research to add the section for SDCL in our EPG. We got several proposals. We contracted with a research team that includes a local consultant based out of St. Louis and the University of Missouri-Columbia to update our EPG to include that. So as Ross and Jason mentioned, if we get this in our EPG, hopefully others will take use of that, just like Jason and Wilson and company did with Oregon's detail. If you want to look at our engineering policy guide, it's in its 15th year, I think. It's epg.modot.org. It's got everything we do in one document there. Okay, so we heard about other states with SDCL projects. Nebraska has 3 bridges, and Ross gave us a detail of those and how they've been performing over the last 21, 22 years, and that's been great. Tennessee, it was also alluded to by Dr. Aziz and Amini earlier that Tennessee has SDCL. So I contacted my colleague Ted, who's the state bridge engineer of Tennessee DOT, and he shared some plans of this is one of them, Massman Drive over I-40 in Davidson County. It's a 2-span at 140 and 147. And I show the details here, the intermediate bents, and we talked about the compression plates and all. In this particular one, they chose to use tapered plates, as you can see here, and they also did splice plates on the top flange. As we've heard through the design considerations, the splice plates, you can carry that tension through the reinforcing in the deck, but they were early on in adopting this and chose the splice plate. I've heard that Iowa has had SDCL project. I was not able to locate any records, but what I'm going to ask here is from our attendees, are there other states, so we can kind of get that on record if you want to put that in the question or chat bridge or chat box. As Jason mentioned, they applied for an alternate applicable standard and found the detail 3620 out of Oregon's bridge manual. If you look at Oregon's bridge manual, their bridge engineering section, section 1.6.2.3, they've got the simple for dead load, continuous for live load documented in there, and see detail 3620, which is the sheet shown here. So those are the other states that are doing SDCL, or at least have some details. We hope to get it in our EPG, as I mentioned. What other states have tried SDCL or use SDCL as a standard practice? And we'd ask that you leave a note in the chat box of the webinar so that we can document this, and Dr. Aziz and Amini can have that for his record of states that have that. when he's talking about this topic. So lessons learned, I'll just kind of recap what we heard over today. And these are really in no particular order, but the Nebraska bridges are still performing well after 20 years. And you heard Ross questioning at the end of his presentation, why hasn't Nebraska done any more of these since then? I hope that other states are considering this. And I hope if any of our contractor consultant partners are watching this video, we are rebuilding Interstate 70 from Wentzville to Blue Springs, which is about 200 miles across the state of Missouri. Wentzville is in the east side of the state, the St. Louis area, and that's where it goes from 3 lanes in each direction to 2 lanes in each direction. And Blue Springs is on the west side of the state near Kansas City, and that's where it goes from 2 lanes in each direction to 3 lanes as it goes into Kansas City. So basically we're making a 3rd lane in each direction for about 200 miles across the state. And so why do I mention that? Because all of the bridges that Ross talked about were 2-span structures, and many of the bridges over Interstate 70 are the 4-span type structures like he showed. So some have been replaced in recent years, others will be replaced as we're doing this I-70 rebuild project. But it would be great to get some steel bridges over the interstate, because when they get hit by an overheight load, steel bridge is a lot easier to fix than a pre-stressed concrete bridge that gets hit by an overheight load. So that's kind of lesson number 1. They're performing well, and they were good for easy to set the girders without traffic interruption over the interstate. So as Ross indicated, can be used with box girder shapes, and I think it was pointed out very well that the box girder shapes that's used with the vertical web, in my mind, seems to be much cleaner to detail and to fabricate and all that than with a trapezoidal box type structure. And I do agree with Ross that those structures he showed with no intermediate cross frames and all were quite elegant. And I'm sure most of the bridge engineers listening, when you're driving down the road, you're always looking underneath the bridge to see what it's like underneath there when you're going and trying to bore your family with details like that. So as Jason mentioned, the design, and Dr. Aziz Amini also, the design concepts are easy to understand for any of the bridge engineers that have been designing pre-stressed concrete. We've been doing it this way forever. Like I said, I think our first pre-stressed concrete beam bridge that was simple for dead, continuous for live, was built in 1961, or at least the plans were 1961. Maybe it was built in 1962, but anyhow, it's something we've been doing all along. And the equations were very simple there. As you see, you've got a compression force and a tension force in a couple, and the distance between them times one of the forces is pretty easy to compute. Gary from DeLong's there basically told us the fabricator's point of view, and I really appreciate his conversation on what a SDCL bridge is not before he started to say what it is. And from the standpoint of the fabrication, less stringent certification is needed. And as he mentioned, you can buy this steel off of the steel service centers. You don't have to wait for special rollings, because generally these shapes are probably hanging around at these steel service centers. In those places, typically they buy 500 tons at a time or something, and if you're going to get a special rolling, you're not going to get 500 tons. So they just have inventory of all the different shapes, so that's good. Cut them to length. The end plates in the compression blocks are pretty easy to do. You don't have to deal with all the testing of the welds and all that. It's just fillet welds on the end. And I like, and we've seen this as well, bridge bundling leads to efficiency. And as Gary mentioned, the first, if you'd only done one of them, they might not have come out so good. But since they had 25 of them, everybody got better at that, and we are also getting better at that as well. And so we've designed some of these, and let them as design bid build, our traditional contractor procurement method, but these bridge bundling packages and design build have also been useful for us. So those are the lessons I think we recapped. I'd be happy to hear any other lessons if somebody wants to pop them into the question box or whatever. So future opportunities, areas of opportunity. Hopefully this in-depth webinar will encourage other states to maybe consider this or look into it. And as Dr. Aziz Amini mentioned in the beginning, investigate using ultra-high performance concrete for intermediate diaphragm details. He mentioned a pool fund study. As I mentioned before, we did one of these on an existing bridge with the Everyday Counts program, Federal Highways Everyday Counts, UHPC, and we did repair beam ends for a simple span bridge that was completed, I think it was in the 50s or 60s. I'd have to pull up the plans. But we did this simple for dead, continuous for live, really as a method to extend the life of the bridge, to also repair some section loss at the end of the beams of the simple span. So that bridge is still in service, and that was done, I think about 7 years ago. So those are future areas of opportunity. Again, I'd like to, if anybody else has ideas, to put those in the question box. And with that, I think I have exhausted all that we want to talk about, and we would welcome all the others to come back and answer any questions that Paul or Kathy may have that were on the docket.
Great. I'm going to jump in really quick. We had a number of questions that came in related to the link slabs versus the simple for dead load, continuous for live load. So Atorad, if you would come on and maybe help us understand that particular piece better.
Let me just say this. The link slab, okay? Seems to be some people believe things that the linkage slab is the same as SDCL. No, it is not. Like I said, many years ago, I remember Ed Wasserman, former state bridge engineer at Tennessee, made a comment that cracked deck over the joint is better than any expansion joints that he has seen. And I think it's a true statement. Linkage slab is meant to eliminate the expansion joints over the pier, not to provide a continuity for live load. SDCL is, by providing the steel reinforcement over the pier, provides a live load continuity. On my screen, I'm going to show you one thing. On my screen, this is a part of the paper by Paul Zia. I believe this is a May-June 1998 issue of the PCI magazine. And he says about the simplified method of analysis. Let me just read this paragraph. Because the stiffness of the linkage slab is much smaller than the stiffness of the girders, the linkage slab introduces a negligible amount of continuity to the structure. Therefore, this is important, each span of the bridge can be treated as simply supported girder, and its deflection can be calculated by neglecting the effect of the linkage slab. So, linkage slab is just to provide, get rid of the expansion joints and have the continuous deck. Now, Paul Zia in this paper, now I'm going to go to beginning of this so you guys will see. This is the paper by Behavior and Design of Linkage Slab for Jointless Bridges by Paul Zia, a distinguished university professor at North Carolina State University. Paul goes, this is additional information. Since Paul published that paper, there has been some additional research. There is a belief, in fact, it is reflected in the AASHTO guide for ABC design, and I have had some discussion with Mark Kulmo, who wrote that. There are some additional research that shows that actually you don't need to have a deep bonding between the concrete and the top of the steel girder over some length. That is suggested by Paul Zia, and that actually was carried out to the AASHTO guide for ABC design, especially if you use a UHPC. What you need to do, it's not a matter of a force design, it's a matter of a deformation. You have to be able to deform, to rotate, basically rotational ductility you have to have. So just to summarize it, Kathy, linkage slab is just to have a continuous deck, get rid of expansion joints, not to provide continuity for live load. SDCL provides continuity for live load. So that's the difference between so there are two different animals altogether.
Great, thank you. Todd, did you have anything else that you'd like to mention about the future pooled fund? I'd like us to get to questions, but I just wanted to give you a final opportunity to talk about
Right.
that.
It is I think, as you heard from it was great to have two state bridge engineers, Baron Ross from the state of Nebraska, and Brian, open-minded, progressive state bridge engineer from the Missouri, and you heard from the designer, from the fabricators, that SDCL is it's a very viable solutions, especially actually when you use the ABC method. And there are a number of different details people have used. Some of them have some advantages and so on. But we've done some numerical work which indicates that we can use a UHPC over a middle pier to connect the girders. And if we do that, we can really simplify everything. No need to end plate, no need for a steel block, no need to have the live load continuity reinforcement to be hooked back into the concrete diaphragm, just a straight bar, narrow concrete diaphragm. And as Brian has suggested, just to have an entire concrete diaphragm basically made with the UHPC. But there are few issues that we need to answer. So we are trying to develop a pooled fund, and some are interested. So what we are asking is that if any state is interested to join in and actually influence the direction of the research, please send me an email. So we'll keep everybody posted.
Thank you, Torad. We do have time to get into some of the questions that we missed during the initial presentations. Paul, if you'd like to come back on.
First question I have here is for Torad, and the question was, how many sets of tests did you do in the lab for your shear and seismic?
For the seismic, now remember that we had done tons of research back when I was at University of Nebraska, Lincoln, to understand the behavior of the system. And for the seismic, the only thing was that we had to make sure that during the moment reversal, because during the seismic event, especially along the length of the bridge, you can have a moment reversal and put the bottom flange in tension. So we had to make sure that we had to modify the detail. And the modification of that detail was very simple. Put a couple of shear studs in the bottom flange, put the tie them together. So we had an extensive study actually numerically, but we had lots of stuff on the background coming from the past research. So we did the component testing, and then we did the shake table test, proof of concept. So it's not the matter of how many tests that we did, but it's a matter of how comprehensively we looked at. So I feel very comfortable, and it was a very comprehensive research in order to extend the SDCL to seismic region.
Okay, another one for you. It says, for the same span lengths, is there a big savings if you design two-span continuous with integral piers caps versus simple span with integral caps?
I'm going to refer that to Jason because he has some info actually.
During our process with the design build, we only really analyzed the SDCL concept. We did not compare what the savings would be with the traditional. So we don't really have hard numbers that we could per se say that how close was it in the end. Based on my experience, or after everything, listen to everybody here, you definitely have to save some money at every little aspect along the way with this concept, if it's a feasible concept to use in your situation. So I want to say at the time, with our project being that it occurred at the end of the pandemic, pricing was a little volatile, and Gary could probably speak to that a little better than myself. Brian and Ross probably have a pretty dang good idea too. But I think at the time, we were around, really $190 a square foot for these things, which seems pretty expensive. But at the time, the pricing was just like we said, steel was crazy. So, but I think it's since come down a little bit. So, but I can't really say directly what the savings is for weight of steel. I haven't gone into that deep dive on that to figure that out. I think it's pretty comparable, but I think more so you're saving on cost of fabrication, construction time, and really design time isn't much different, like I said. So a little bit of design savings.
Okay, we have a couple of questions about the compression blocks. The first one is the distance between, you said the compression blocks didn't have to be touching. But the question was, wouldn't this cause the concrete to either crush or have a void, causing the system to not work properly?
Let me take on this one. We have some test results, and in fact, we had some tests where there was a gap. Remember, detail 2 that we had, detail 2 didn't have any compression block, and it gave a pretty good results. So test 1 is the one that had the bottom flange continuous. Detail 3 that I showed was the one that had just the end plate but no steel block. Still, that gave a very good result. So that's why I don't feel too uncomfortable, even if you have a 1-inch gap in there, because what will happen is that 1-inch gap is going to be filled with a paste, some aggregate maybe, okay? And even if it crushed, I mean, first of all, it's not going to crush. First of all, you're way inside the concrete diaphragm, and the whole thing is confined. So there are 2 things that are working for you: the confinement from the surrounding concrete, and that you are inside the concrete diaphragm. You're not at the edge of the concrete. So the short answer to that question, don't worry about it. Even if the plates are a little bit off, for example, they're not the same size, that's not going to get me excited, because I have seen some good test results. So that's not an issue.
Okay. Then the other question on that block was, could you use a hollow square section for that block, thick walled section, just to save weight?
Well,
You want condensation inside? I don't know, man. That might lead to some issues.
Well, the other question was, how would you seal it? That was the other part to it. That's fine.
I mean, you got steel stay in place forms. You fill those low points of the form with polystyrene, and I suppose maybe you could throw a polystyrene in there if you wanted to. I don't know, Gary. What's the price difference between a 3x3 hollow tube and a solid bar?
Well, I mean, I don't know. I do know that tube is substantially more expensive per pound, but then when, if you're using a 3.5 by 3.5 by half or something tube, and you take out the center, I don't know where that would be cost wise. I know that the welding is a little bit different because you've got rounded corners on the tube. I like it the way you did it, Jason.
Okay, that's
Me
good.
too. Me too.
That's fine. All right. The next question was, is the partial depth diaphragm poured prior to the deck necessary? Some details seem to show it partially poured, while others seem to show it poured entirely with the deck.
I can take, absolutely, you do need that, because the end of the girders have to be secured against the rotation. And Brian and Jason showed the very good detail where you put that steel, even cold form steel, I mean, very thin, in the center of the concrete diaphragm, that basically you pre-crack the diaphragm. And if you do that, if that plate, you can fill it to 2/3 even, that shouldn't be no problem. The one that we had problem, the Ross showed, the one in the Grand Island, that was the first time that, and I was on the job site actually. I remember that's the way I used to have fun, basically go in the middle of the night to see the casting of a deck. So I was on the job site and they were pouring, and then all of a sudden the concrete diaphragm, well, the concrete diaphragm had been poured, they were pouring the deck, and then all of a sudden the contractor saw that there was a cracking taking place, very random cracking, because we didn't have that plate. So, but you do need to fill the concrete diaphragm because you're eliminating the need for the cross frames. But if you put the steel plate that Jason showed, that Missouri have been using, you won't have the random crack and you will be fine. But you have to have that concrete diaphragm half 2/3 filled. Yes.
Okay.
Let me expand on that. I want to ask one question. So I know there was an option. The contractor said, let's not do the end diaphragms at the intermediate bends, and let's go ahead and do the partial height pour, right? But they could have opted in doing that, and we could have stabilized the end beams and then poured the diaphragms as one. We would still put the plate in there though, right, to control the cracking potential?
Yeah. Pouring the deck and the concrete diaphragm at the same time?
Yeah.
No, because you remember when you pour in the deck, right? Think about the lateral stability of the compression flange. You have a simple span. So the end of the girders have to be secured. And if you pour the deck and the concrete diaphragm at the same time, no concrete basically in the no hardened concrete in the concrete diaphragm prior to pouring the deck. I wouldn't advise that, because then you're looking at the end of the girders being not secured against the rotation. That's what you're asking, right? No, you have to have at least a half of it. You can go to 2/3 if you have that steel plate that you use.
Okay, let's get one more question. Bridge is skewed. You have them there together. Tord, you said that it works. But the question was, do you have to skew your screed if you have that to keep your deflections working together?
You have to skew.
Does the screed have to follow the skew as you pour your concrete?
It looks like Jason knows what they did on the skewed ones.
Yeah, I think so on farm, we use a vibratory screed, okay, which is unusual. So it's not the full weight of a larger screed machine. So we had fairly low weights being introduced into the overhang bracket. But assuming, I think we required them to at least place the concrete along the skew if they did not also skew the screed, if that makes sense. Now, if you do this, I don't know what they did in Northwest, if they ended up using a traditional screed machine or not. I don't think they probably did. But these shallower beams, you got to be pretty careful on that.
Okay, we're at 3:17. So Kathy, I'm going to turn it back over to you.
Thank you very much, Paul. So we're now at the end of our 2025 in-depth web training. Thank you everyone who has attended and for hanging with us till the end. On the screen, there's just a quick reminder again about our engineering conference, our World Bridge Engineering Conference in 2026. Thank you to Paul Lyles for moderating the Q&A and to our FIU staff for managing the web room. And thank you very much to all of the presenters and those who attended and contributed to the sessions with questions and answers. With that, we will conclude our in-depth web training. Thank you very much.